from few microns to say some hundreds of microns, okay, or even some thousands of microns or kind of a range. Okay, so we'll talk about some of these devices. So why this MEMS is becoming important, or how this has evolved. So see see, these are like different chips and number of transistors per chip. Okay, so you can see Pentium already is in 10 to the power 7 number of Pentium 4 if you talk about, okay, that kind of a size range. Okay, so many transistors you are having on this single chip of maybe 1 inch or 1.5 inch square. Okay, so how people pack and fabricate so many transistors at a time in a single kind of a chip. And like some of you may be knowing that technology, but the idea is, so if you can fabricate electronic components, why not mechanical components? That's where the MEMS started. Like, okay, why don't we kind of put some kind of a moving components on the chip, and like have some interesting systems developed out of that. Okay, so that's where like this roadmap for microprocessors or microcontrollers is important to kind of see. Okay, right now people are already fabricating devices at so many 10 to the power 9 number of devices on a single chip. And now if you talk of this dimension, like you already are touching nanometer kind of a scale, so you can get nanometer size mechanical components also possible to be designed on the chip. Okay, so now so these are what like this is how the technology is scaling. The number of devices is scaling up, a number of transistors on a chip, and the size of these transistors device like getting down. So you can have like laptops as powerful as like desktops previously or workstations previously, and now with the advancements in the technology, you can have the same kind of a capability in your like smartphone, and the chips of like smaller and smaller size. Okay, so as we scale down in size, we'll be able to fabricate the mechanical components of that size as well. And how do we use them then? Okay, what is a motivation to fabricate such kind of a components? We'll see that in a minute. Okay, so see these micro size systems. Suppose we talk of sensors, for example. Okay, so all of us have used some or the other sensor. Okay, the sensor main functionality is to sense the environment. It is, say suppose for example, temperature sensor or accelerometer sensor. Okay, so you have a temperature to be sensed. You put it in an environment where the temperature is to be sensed, and the sensor is supposed to kind of take only little power from the device, okay, or from the phenomena that is being sensed. If sensor itself starts taking a lot of power out of the phenomena, then the phenomena itself will change. You see the point? So we don't want the phenomena to change, but we want to sense as it is, what it is. Like we don't want to perturb the phenomena at all. Okay, and that's where like we want to, the sensor should consume very less energy and give us a sensitive kind of a reading output. Okay, and that's where this MEMS comes in picture. So these MEMS devices or nano devices will hardly need any power to kind of power them up. Okay, so say for example, if you are having a MEMS temperature sensor, okay, it will hardly draw any from the environment where it is sensing, and still it will be able to give you accurate reading. So this is one kind of very important aspect, that okay, it has a higher sensitivity, accuracy, and maybe selectivity. Okay, the selectivity is like comes based on the spatial location. Say for example, if you are talking of temperature, I want to know temperature exactly at this particular location. Since MEMS device MEMS sensor is very small in size, it will give you the pinpointed location at which the temperature is to be known. Okay, so that's how like you see that these devices have these extra advantages that you will not find normally in our sensors. For example, if you talk of our thermometer, okay, versus the MEMS temperature sensor. Thermometer can sense like big size environment, okay, but I want to kind of like know exactly from 1 mm apart from that position what is the temperature. I'll not be able to kind of get to know that based on the thermometer, for example. That's where these MEMS temperature sensors could be more selective or accurate. Then, as I said, less energy withdrawal from the application. That's why, like, no, it will not perturb the application too much. Then, this is one very important point. Like, see why this. See what what technologies are getting driven by the market, or they become popular and accepted by the industry. Thought of over this. Okay, what kind of technologies people adopt, and like, these are the disruptive technologies. So the technologies that give you more productivities and and effectiveness or performance, okay, those technologies, but at the same time, this is available at a lesser cost, okay, then it will become very popular, okay, and that's what exactly happens here. See, this computers were there for a long time, but MEMS started coming up only now because the cost of fabrication of the chip now is much lesser as compared to what it was earlier. Okay, and this cost advantage gives like the different kind of a dimension for this technology. So the technologies which have like lesser cost and give more kind of a productivity and more kind of a performance, those technologies will be taken up and absorbed by the market, and then they'll flourish, and people will start doing research more and more into those kind of aspects. Okay, that's how this typical science and technology evolved. I mean, there are some scientific phenomena people study from academic perspective alone, but most of the research is like funded by like industry. There the research goes in the direction, or technology development goes in this direction of what is going to be useful for society in a immediate run or a long run. In increase performance and like decrease cost. And why this decreased cost? Because they are produced by this bulk processing. We'll see what is this bulk processing means. Like, see, one can fabricate millions of transistors on a chip, single kind of a wafer of silicon. Now the same technology can fabricate so many millions of sensors on the same kind of a platform. And those sensors now, per sensor cost, if you calculate, that will come down drastically. Okay, that's how like this bulk processing of all the sensors together at a time on one single wafer is what is referred to as bulk processing. Then more sustainable reduced risk and provide high capacity digital storage also, like this MEMS kind of a sensors will, or systems will have storage on board possibility and things like that. Okay, so this is very important, that it gives many new features and products which were previously unthought of. So as I told, this kind of a contact lens which can give you like all the information directly into your eyes. It's like a Google Glass, but it is inside your eye now. Okay, so not really just, you don't have this kind of a big wearable to wear and then see through that and like do that. Instead of that, this is now packed up in a very nice kind of a compact form, which is like a contact lens kind of a form. Okay, so these product, maybe 5, 10, 15 years down, like before, it was definitely, maybe it was not at all thought about. Okay, but the things which are not thought about, and they are like really becoming in reality nowadays. um, so we'll see some of these applications of these MEMS. These applications are in many different areas. Okay, I'm listing some of them here, and we'll talk about a couple of others also. Um, so medical devices, medical MEMS, then automobile, lot of sensors go in the automobile domain. Then in aerospace, there are a lot of sensors that are coming from the MEMS devices. Then you have a bio-MEMS big area actually. A lot of biosensors nowadays coming up in this area based on the MEMS technologies. Then chemical sensors. Then you have a wearable sensor that are coming up. Wearable electronics and wearable MEMS is another kind of a buzzword that is coming up nowadays. So these are some of the medical applications. So you can see this smart contact lens that I was talking about. Then some of these now can be used for the diagnostic so see, if you have something which can be wired and put into your contact lens, I mean the same thing can be sensing the condition or the health of your eye, and then it can diagnose this glaucoma and other diseases at the early age. Okay, then this is a smart pill. It's like a pill that you swallow and then it will travel your canal, okay, the digestive canal, and it will start taking pictures, intermittently. And those pictures will be sent to your computer or like, mobile phone, and for you to kind of diagnose and analyze. So without any pain for this endoscopy or colonoscopy, you are now able to image the inside of your body in a very smart kind of a way. Then these are like implantable, some sensors for activity in the brain. Then you have this implantable blood analyzer, and then there'll be some kind of a the drug delivery system also can be possible based on the condition. Okay, so say for example you can have a insulin sensor and insulin drug delivery system in single package which is implanted in your body. Okay, and that will keep on monitoring your sugar level and automatically carrying out the dose of the insulin as the body requires it. Then in the automobile, you see that there are these chips which are used. Now the companies have their own kind of chips. Also, there are this company called Analog Devices who produces these accelerometers which are used to sense the acceleration of impact, and then based on that acceleration, the airbag is popped out to save the driver, or like the passengers from the accident injuries. Okay, so this is one of the important applications in the automobile. There are many different other sensors that are there in the automobile. Okay, so for example, you see that there are some sensors. I mean, I have listed here. Okay, one can go through and so nowadays these all these MEMS based sensors, acceleration sensor, or some of these are not really MEMS, but some of them are miniature kind of a sensor, so to say. Okay. So these sensors they power up the automobile for example to have possibility of this autonomous smart driving. You can see one video here. Just to give you some glimpses. I mean, it's a big video, but like you can look at it later. So let's see if it is popping out. Please, I'll have to share this screen. Huh? Yes, right.
Just to play, sir, it will come. No problem.
I can see Andre. Is the screen sharing working?
I hope so. Let's try.
A lot of introduction.
Yes, I'm very excited to be traveling incredibly quickly and with very high kinetic energy. And we are putting meat in the control loop into the system. And so this is quite undesirable. And really fundamentally what it comes down to is people are not very silicon computers have significant
Sir, you can unmute, sir. But the voice is not coming.
Wait a minute. No. Unmute only. Okay. Okay, maybe it is taking the video. Okay.
Okay, you play. You can play, sir, now.
Wait a minute. So can you hear me now?
Yeah, I can hear you, sir. Okay.
So I think this video voice, when it is going there, no, I have to pause from the Webex buttons. Okay, so what I was saying is, like, this computer has a better kind of a reaction from the perspective of car driving than a human being. So that is what is listed here. So whatever this human being has, like, 250 millisecond reaction latency versus computer has 100 millisecond. Then you can see only at one direction at a time. Okay, but when you have a computer with 8 cameras in particular in this Tesla car, all over, you have a 360-degree awareness of somebody is coming or walking behind here or side or whatever. Okay, so this is actually now coming up in a big way in not in India yet, but many countries otherwise. So, for example, you'll see in this video some of the test drive conditions where, like, this will be seen nicely. Okay, so let us see this.
Low latencies. They have 360-degree situational awareness. They are fully attentive and never check their Instagram, and alleviate.
So
actually,
this
this
is
a pretty,
like
present prediction. So what I think is kind of unique.
So this is like, a classical thing. Okay, these kind of questions may be there in the future. This is like a more kind of a futuristic stuff. You don't need to drive by hand. Okay, you can drive by wire, like, or you can just, like, you program the system to get, and then the system will take over and, like, it will drive you wherever you want to go. Okay, so let's see some of the situations, how in actual practice people have been looking at these situations. Okay, so you see this
Over sort of during the day. So here's an automatic emergency braking scenario. So the driver here is proceeding through an intersection, and you can see trouble coming here. So the person kind of crept up from here, and the car sees the pedestrian, object detection kicks in, and we slam on the brakes, and we avert collision. Here's an example of a traffic control warning. So this person is probably not paying attention, potentially on the phone, is not braking for the traffic lights ahead, but we see that these are relevant traffic lights. They are red, and we beep, and the person immediately starts slowing, and probably does not actually enter the intersection. These are examples from pedal misapplication mitigation, PMM. Here, a person is unparking from their driving spot, and they are trying to turn, and then they mess up, and they accidentally floor it. So they floor it right there, and the system kicks in. It sees pedestrians ahead of us, and it slams on the brakes and averts what would be a very gnarly situation in this case. Here's another last scenario I can show briefly. So this person is trying to park, and they turn to the right here, and they intend to press the brake, but they actually floor it. And the system, again, says that there's no driving path forward, and actually slams on the brakes and averts. In this case, this person is not going to be swimming in this river imminently. So these are some examples of the value that we are providing today in this incremental autonomy.
Okay. So you saw these scenarios. They are not like a what you say, virtual scenarios. These are actually practical scenarios in the car. They have designed the car which will kind of, like, take care of these issues, and they are testing it out in a real world kind of scenario. So Tesla are quite advanced in this kind of progress for. So this uses a lot of these sensors. Like, you'll have actually, like, there's inertial sensors. You'll have radars. You'll have the cameras and vision sensors, and then there is a lidar kind of a sensor. People are using a lot of these kind of different sensors, and actually this application is happening. You can see part of video here, and it will be kind of we'll stop there. Okay, so you can search for such kind of videos, and you'll find that. So you see this. So the,
Hello, sir. The video is not
intersection. And this is actually a pretty old video, I believe.
video is not getting seen.
Now it is playing, sir. Now it is playing. Now once again you off it, sir. Now it is stopped.
Okay, yeah.
And so you've been seeing stuff like this for a very long time. So
Okay.
what is the big deal? Why is this impressive? And so on. And I think the important thing to realize, and that I like to always stress, is that even though these two scenarios look the same, so there's a car taking a left at an intersection, under the hood, and in terms of the scalability of the system, things are incredibly different. So in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor.
So we'll pause here now. Okay, we'll pause here now, and then like I'll unshare the screen and share the other screen. Okay, so what I was talking about here is like this the application of okay. So this mechatronics and MEMS, they are not really like different kind of things here. Okay, so MEMS and mechatronics, they go hand in hand in many different kind of systems, and people have made use of these things now with the power of computation and artificial intelligence, machine learning kind of a thing. You can now realize like these kind of a complex kind of a scenarios of car driving autonomously. Giving a reaction to, say for example, otherwise the driver would have not missed something that now being sensed, and car takes over, and it so even if the driver is driving the car, if it is in this autonomous kind of a mode of driving, then some of the scenarios will be prevented, and that could be used just as a teaching for the driver, okay, or driving school kind of a teaching. But anyway, there are a lot of these kind of interesting possibilities coming up in this automobile area, just to give the sense of it. Of course, in the aerospace applications, you have a lot of these sensors being used, especially inertial kind of navigation systems now becoming miniature. Small inertial navigation systems are useful in many of these defense and aerospace kind of a domain. So these are inertial sensors that you can see here. The space exploration, you need the smaller and smaller sensors there or smaller systems there to make sure that the weight that you are carrying out or that is to be propelled in the space is minimized and things like that. Okay, you might have seen this interesting application called Segway. Okay, so here it is like a two-wheel kind of a car, and this has like 5 gyroscope sensors in this bottom here. Okay, and it's all driven by this inertial kind of a navigation or inertial sensor system. Okay, it's not really navigation. Navigation is based on the person's response, and this system you just sit on it, and then you or stand on it, and then you push yourself or lean on one side, and it starts driving in that direction. You want to brake, you just lean backward, and it will brake. So it's our human responses, whatever we happen, okay, oh, I'm going too fast, I'll just slow down, I'll just go back, and then this system will slow down. Okay, so this is built in really very nice kind of a way, and it is already in use by the police department and the post office departments in the United States. Okay, Is a bike that was designed by a Canadian designer. He was just 18-year-old, but when he was visiting China, he wanted to kind of give some solution to ride roads in there where so much of a traffic jam is there, and nowadays they have systems which are like very tiny kind of a two-wheel kind of a system, and now so this is typically having this kind of a mode. It has a, in this kind of a configuration, it has like a slow speed, but it can turn these two wheels. Now one wheel can move back with respect to other, and that can give you other kind of a configuration, normal configuration, that can have a higher speed. So you can have this changing configuration to drive in the environments where you have more or less traffic. So that is a very interesting system. You can look at this in more details, and all this is kind of powered by these MEMS gyroscope sensors. Okay, so that inertial sensors are there in the bottom. Then these are like encoder system. Any question? Am I audible?
Yeah, you are perfect, sir. No problem.
Okay.
Audible, everything.
I think my screen was not full probably. So now these encoders gratings are like these 81,000 grating lines in the on the disc of 36 kind of a size. Okay, and it is these kind of a grating lines are useful to give you like the rotary position of this axis rotation shaft with a very high accuracy needed for many different applications. And then they use some kind of a phenomena of diffraction of light or interference of the light to get to this kind of a sensing. Then these are the BioMEMS sensors. These are the cantilevers which are fabricated in IIT Bombay actually. So these sensors will have this some kind of a coating on the surface, which is antibodies are coated here, and the antigen in the blood sample, when it interacts with these antibodies and get attached, there's a change in the mass, or then there's a change in the surface energy of this cantilever, and that is what is being sensed to detect that okay, this particular antigen is there into these antibodies. So these MEMS based sensors are used in that kind of a principle to so you can look at the frequency of this vibration of the cantilever that is changed because of the mass or surface energy interactions, or you can have some kind of a piezoresistive layer on the top which shows a small change in the resistance as the interaction happens and the cantilever actually bends. Okay, so there are many different kind of techniques you can have. The optical techniques can be there also, or resistive sensing techniques also can be there in the MEMS area. This was a capsule that I was talking about from other company now. Then these are sonar kind of applications where you have ultrasound, these capacitive micromachined ultrasonic transducers are there. So these are ultrasound transistors. So ultrasound, as you know, is used for many of these, looking at parts inside the body. Okay, you do some sonography to do this ultrasound. So that is one of the applications for such a kind of, chips which are now at a miniature kind of a level they are produced, and then they can be also useful in the so you can have an area of such a kind of a ultrasound receptors also and transmitters also. Okay, and then this transmitter receptor combination will be able to kind of drive different applications. And one of the other important applications is underwater kind of communication that happens through the sonar. Okay, or this ultrasound transmission underwater happens through these waves, and then it is received by the sensor, which is ultrasound sensor. Okay, and these are the key features that it provides larger bandwidth. Then higher frequency operation is easier because it is smaller in dimension. Okay, this is like micro machined by using like the VLSI kind of a technology. Okay. Then this ultra compact MEMS FTIR kind of a spectrometer is other application. So where you have this mirror which is actuated by MEMS actuators. Okay, and that is used for the detection of the spectrum. Okay, So this is so all this, whatever this FTIR, like Fourier transform infrared spectroscopy, that is done in a miniature kind of a form. Okay, and that's what is gives you a lot of key features of this high resolution, then high throughput. You need lesser amount of space and energy to do that. Okay, and this is like a portable kind of a device can be made to do on-site spectrometry. Then there are chemical sensors which are bio-inspired, people use. So if you want to detect contaminants, and you have these olfactory sensors, the way the dog senses the different smells, like that you can have the MEMS sensor developed to do the similar kind of a thing. So you'll have some kind of a, typically the sensors will have some electrodes, and they are joined by some kind of a sensing element. Sensing polymers typically are used for sensing, and so this is some kind of a form of an array of electrodes, and then there'll be this network of polymers that are used here between the electrodes, and as the polymer absorbs some of these gases or some of these chemicals, then the conductivity property of those polymer networks would change, and that will give you sensing. For example, you can use carbon nanotubes in these polymer matrix to do the sensing. The nanotubes are very sensitive to these gases. When the gas molecules adsorbed on the carbon nanotube, then the conductivity property through them starts getting affected, and one can have the sensors developed in that way. So some of the sensors developed in that fashion would have possibility of now detection of the breath. See, the human breath has a lot of these different chemicals that gets released, were particularly disease specific. So if, for example, if you have diabetes, okay, then the acetone levels in your breath will rise. Okay, and now if you have these miniature sensors which can detect the breath and analyze the breath and detect what are chemicals are there, now you without the blood or blood sample in so intervention of the blood sample testing, you can predict about the diseases in the body, and that is what is coming up now big way in the so you may not be, it may not be surprised if you find some devices which are just you have a mobile and you breathe into that, or you have some kind of a device in which you breathe and connect to your mobile, and you get the list of problems, or upcoming kind of a problems that you might have. So the health monitoring systems scenario is going to change now. Instead of doing some kind of a diagnosing the disease and then treatment of the disease, now there'll be a preventive maintenance kind of a thing will come up, where you have this big data of this, if for the health data of a person collected from either from the sweat. There are some chips which can sense the sweat chemicals and then do that, or this is a breath sensing. So this is one of our companies that was mentioned, Virtual Sense Global Technologies, is looking at a breath of a person and looking at some chemicals into that to detect this, particularly say the diabetes kind of application, and then this can be extended to many other kind of diseases in the future. And just monitoring this takes hardly any kind of effort or time. So if you are monitoring these daily on a daily basis, your breath, okay, see, monitoring your blood sample daily basis is going to be very tough, but monitoring the breath daily basis is very easy. Okay, so that's why you breathe once or twice in this device daily, and then this device will advise you, okay, what is that you should do. You are supposed to do more exercise now, or you're supposed to consume something or not consume something. All these advisories will be coming up from the big data, or from this analysis of the data of this breadth over some time period. Okay, so these are like futuristic systems that are coming up, and it's not like too much in the ahead in the future. I know while we are alive, we may see some of these technologies coming. Wearable MEMS is another kind of a big area that is now coming up. You already have these different Fitbits and bands and this Apple Watch and a lot of these things which are having this you see this sensor that it has accelerometers, it has gyroscopes, it has magnetometers, it has a pressure sensor. These are all MEMS sensors. Okay, it has some small microphone, then temperature sensor, then conductivity sensor. This then of course you have camera, optical sensor. Then there are some micro speakers there. So these speakers are different than our normal speakers. Okay, these are like a MEMS chip on which these speakers are like the small elements which are vibrating. Then you can have this e-nose. Okay, this is coming up now. Okay, that is what I was talking about, that it is a breath sensor. You just it senses the gases or chemicals around in the environment, and then pH sensor, humidity sensor, and so on and so forth. Okay, so these are like many different kind of a sensor that already are embedded into the system, and many of these are like based on the MEMS technology. And there are so many applications you can see. We already are, some of you are already knowing or like using these devices to monitor our health and fitness. Okay, so the point is that the healthcare scenario is changing a lot these days. Like people are becoming more aware about these kind of health monitoring systems are making people more aware about the health conditions, and the preventive maintenance is probably the key for the future health support systems. This is our normal inkjet printer nowadays. Like it is going now absolute. Like not many people are like getting into this using this inkjet printer because of the laser printers are available at little higher cost, but not prohibitively higher. So this ink but this inkjet printers are very useful to print the electronics on the flexible substrates. Okay, so instead of like the normal ink, if you use a silver ink, for example, then whatever you print becomes a conducting line on the substrate. Okay, that is the kind of idea people are using, and like a lot of this printing technology is now getting into the domain of electronics on flexible chips, flexible substrates, and things like that. So that wearable electronic sensors will have similar kind of a flexible substrates. Okay, this work on a very simple principle. Okay, that it has this small little kind of resistive elements here. When you see these lines that are coming up, so this is from our own printer cartridge. We have like scrapped it and like looked under microscope what it has, and you will see this. So don't think these are like some of these things are out of our reach because of the lab facility or like another kind of a thing. That is another notion that people usually carry, that mechatronics or MEMS, we don't have like big labs as good as in IITs, and like how can we do the research in this domain? No, I think that's whatever we have around. If you just look at the things which we have around, by using them, we'll be able to kind of do some things at least to some extent. When I talk about fabrication, I'll tell you about like a little more about some of the systems that we have developed in-house without using any kind of a high-ended MEMS fabrication kind of a facilities. We have built our own kind of a systems or mechatronic systems to kind of fabricate MEMS devices or micro-scale kind of a features. Okay, so we'll talk about that in the second half of this lecture. But so this inkjet printing is that way a very cost-effective technology that is available at your hand. You can use this. There are some printers which are available where you can put your own inks there. Okay, you can use your own ink preparation and then put it there, and then you start printing, and then there'll be like a functional electronics you can print, or you can have some kind of a polymers which are printed, which will have now this gas sensing that I was talking about. Okay, so that can be done by this kind of a printing of the these electronic circuits, or you say the sensor circuits on some small chip area. And then you can, so this is a very good, very low cost kind of a way of like getting into, making these kind of a sensors which will work really a good kind of a thing for many different applications. Say for example, you have a silver electrodes and connected by some kind of a polymer matrix, it becomes like a gas sensor. Okay, you use some carbon nanotubes in that, or graphene in those polymers, and then you start kind of printing those. And you will see there are tons of literature or papers that are coming up in that area nowadays. How we print graphene and other kind of chemicals on the paper or on any flexible other substrate. Then this is like a optical fiber switching application where you have a small little micro mirror which still, and like when the tilt is happening, this input coming from this fiber, instead of going to this fiber, it may go into other fiber. Okay, these optical switches are needed for a lot of these your internet applications where you have the data transmission happening from different place to different place. Like that, you need to kind of route your data to different places. Like when there is optical data that is coming from optical fiber, you need to kind of use these kind of arrays to do the driving of the signal from one place to other place. Okay, the optical signal is diverted from one place to other place. And these are other kind of a MEMS chip where you have this mirror which is popping out and which is going in. You'll have a direction of the optical signal changed on chip. And then this you can have then this multiple kind of array of such a gimbaled mirrors. Okay, so these are gimbaled here, so that the mirror can turn in this direction or in the X direction or Y direction, and then give you this kind of switching in a fast way. Okay, this is very established technology nowadays in the optical switches. Then this is one of the very first kind of applications where the people in this Mergani at MIT developed this micromotor. Nowadays it's not much used, but it was just an exciting thing at that time. How at such a micron scale, you can see the scale is 50 microns here. At that scale, you are developing this kind of a small little motor. Now you start running this motor and it will run at really high speed, because now there is hardly any inertia for this motion to happen. So those who are in mechanical domain, like big size things like have a bigger inertia, and to rotate them at the speeds of 1 lakh RPM, it cannot be unthinkable thing to have. But these motors at micro scale can run at 1 lakh speed very easily. Okay, of course there is a lot of wear and tear will happen in this bearing here, and this motor will burn in no time. Like you start, it will run for maybe 1 or 2 minutes, and it will kind of all this thing will got worn off actually. Okay, so but this is interesting, one of the first interesting applications people see. As we start off with developing such a systems, you'll typically do like that. Okay, you'll have something which is not much useful, but it is just some different thing that was not there before, and then people start, like, that is a cue that people start now learning from that and develop that knowledge, and now develop now micromotors which will be functioning much better than this motor that was fabricated before. Okay, so there are comb drive based some motors people have developed. Okay, so this principle of working is similar to the stepper motor, is what I wanted to say here. So we are doing like mechatronics course. So in the mechatronics part, we'll definitely look at the stepper and servo motors in more details. So this is again application of mirrors. Now we are all talking about many different applications of mirror. So you have seen this you have heard this name called DLP. Okay, so this is like a digital light projection system. Okay, so the way you see now, like your LCD projector was a previous technology. Like that, DLP projector is coming up as a new technology in the domain, and these DLP projectors are getting more popular because they are very compact in the size, and energy consumption is also less. What they do is basically they have this big array of small micro mirrors here. And those micromirrors, each micromirror will have 4 electrodes below that. This yellow thing that you are seeing is electrodes. And then you switch on this electrode, and then the mirror will get, like, this is a capacitive kind of a actuation will happen there, and then the mirror will tilt in that direction. Okay, you switch this. Hit my pointer. Then if you switch the other yeah. So if you switch the other kind of electrode, you will start tilting the mirror in other directions. Like that, you can tilt the mirror, and like the light that is falling on the surface, you can pass it on the screen or not pass it on the screen. Okay, and that way you'll be able to. And this happens in like fraction of a second. I mean, it is a few nanoseconds kind of a response time will be easily for this kind of mirrors which are like deflecting the light. And this gives empowers, like now so 1 pixel on the screen, okay, or on the surface where the light is getting projected, the 1 pixel will be controlled by this one mirror. Okay, like that there are thousands of mirrors controlling thousands of pixels at a time, and your entire image is getting projected on the screen. And you'll naturally ask, okay, oh look, where is the color coming here? So what is done is, like you use a color wheel before the light falls on this surface. So when the green light is falling, this color wheel will make the green light fall on the surface, or red, green, blue, 3 kind of a color filters will be used in that color wheel, and the light will be passed through each of the filters. So when the green shines on the surface of the mirror, some of the mirrors will be projecting at some point where the green color is needed, and or some mix of the color is needed. Like when the red color comes, like part of the red also will be falling on the same place. Then green and red mixed color will be projected at that particular point on the screen. So like that, this is the idea that is used for DLP projection actually. Okay, and it is powered by all these MEMS micro mirrors here. Okay, and see, this is how it will look like. Okay, so this is like a red, green, and blue kind of a color wheel, and it is falling on this digital. So this is called DMD, or digital mirror device, or like the digital light processing kind of a chip is the other terminology that is used. And they are now using this to kind of like to project it on the screen. So do you have some kind of optics to project it on the screen, and you'll see these different colors. And so the way LCD works, it's very different technology from LCD, but it gives a much kind of a compact and lesser cost kind of a same output. Okay, and so see, this technology was being developed by Texas Instruments for like over 10 years without anybody knowing that they are developing, and then they launched this chip in the market, and it was suddenly kind of like, okay, big kind of a wow feeling, okay, that these kind of things can be possible. So these chips, by the way, are available now also at a very low cost. You can buy them, and like you can start doing your own stuff with these chips actually. Very easy to do stuff actually. And there are some chip drivers, and everything is available if you go to Texas Instruments site, you'll find these DLP chips very easily available in the market. And people are using this now for DLP printers, where you project this light and print, like you cure some resin layer by layer, and you get a DLP printer out of this technology. Okay. So these are like more about micro actuators, comb kind of actuators. So typically in the micro scale, you'll find this capacitive actuation is much predominant than your electromagnetic or hydraulic kind of or pneumatic kind of actuation. Okay, so electrostatic scales better in terms of the force per unit volume that you have here. So that's why electrostatics is used here. So there are these two kind of sides where this comb kind of a structure is used to enhance the area of electrostatic interactions between the two sides. And as you apply the voltage relative to one electrode here with respect to ground on the other side, you'll see that this kind of starts attracting by electrostatic force. This one side comb will get into the other side of the comb. And this is a chip that we have fabricated long back by using this MEMS process. Okay, so that's a fabrication process that is available for multi-user kind of a MEMS processing. So they have typical fabrication steps. Maybe I'll talk about that when we talk about fabrication. So this chip fabrication also is one of the low cost thing that everybody can, all the colleges can afford to do actually. So this is you buy some small area on that processing, and then you have your own kind of mask layouts given, and they'll print this for you, and then they'll fabricate this for you for your small little kind of instead of entire chip processing cost, you will just paying only for the small area that maybe 1 mm by 2 mm, 1 mm by 1 mm area, that is one single chip kind of area that you are paying for, and that cost comes down quite a lot. Okay. So this is like a quick hands-on MEMS if you want to do this. This is a good thing to do. I think there's a video here. So oh, sorry, it's not playing here. Huh? There is some video was there. Okay, anyway. This is another very interesting micro mirror application. I was there at UC Berkeley in 2006, and then I had an opportunity to interact with this Dr. Milanovic from this Adriatic Research Institute. And that time they were developing, and now it is that time it was just in some kind of a research and development kind of a stage. They are developing these kind of a micro mirrors, and I helped them for some kind of a signal processing part of it, and kind of was interested in seeing if it can be done in a closed loop and all. So he sent me some of these micro mirror devices that are there in our lab, and these are very interesting mirrors. I'll show you these videos and it will be clear. Let's see. I'm wondering why this is not playing here. Huh? Okay, maybe I'll play offline here. Okay. So you can see first laser draw. Okay. Okay, can you see this video screen?
Sir, can you minimize that PPT, sir?
I'll just maximize this screen.
That video, it is not running, sir.
Now it is running?
Yes, sir. It is
Yeah.
not started, but it is
not started. Yeah, it will start. Yeah. You see this kind of a laser is directed by this micro mirror chip, and then you get these kind of figures to be drawn. Okay, so this is a single laser which is falling on the surface of this micro mirror, and that micro mirror is tilting. Okay, I'll show you that micro mirror tilt, how it happens. And it can draw such kind of a figures on the wall. Okay, and people have started using this now for different applications. Some of the applications I'll show you, but this is just kind of fun that okay, you can draw these kind of images. These are very good for teaching purposes. One can start using these. You can project this on the screen, and different kinds of images can be wire drawings can be projected. Okay. So how it is happening I'll show you in a minute, but you can have these different possibilities of things coming up here. Okay, so let's get to the little bit how it is happening now. So let's get into this different video here. So you see this is other video. It will show you.
That video is not playing, sir. It was not coming.
This is okay. First video, did you play?
Is not came, sir. It has not played.
Oh, it has not come, huh? Okay.
Uh-huh.
So I'm wondering what is. So can you see the screen at least?
Yeah, we can see your PPT screen, sir. That micro mirror.
Oh, you're not seeing the video screen at all.
No, sir.
Oh, wait a minute then. I think I have to kind of unshare and share again, maybe. Sorry, I think. So maybe I'll share my entire screen now. Let's see if that works. I'll share entire of my screen instead of just a PPT. Okay, can you see now?
Yes, sir. Now video we can see, sir. Now we can
Video part you can see. Okay, maybe then
yeah.
previous video I'll just play first, and because this will make sense only if you see the previous video.
Yeah.
Okay, so I'll show that again here. Okay, this was a previous video. Let me get into full screen here. Can you see now the video in the full screen?
Yes, sir. Okay, sir. Clear, sir.
Okay, clear. Okay, so now you can see this video. Okay, so these are the figures, different figures that I was talking about that can be drawn. Okay, I'll just fast forward a little bit. So these different kind of figures can be drawn. Now what is happening is, like, the laser is falling on one single kind of a mirror. The mirror is only one there, and then that mirror is deflecting and diverting laser to kind of draw these figures on the ball. Okay, so this is a green laser light that is used to kind of do this activity. Okay, so you can see different kinds of figures that can be drawn very nicely. Okay, so now let us see how things are happening here is by using this gimbaled mirror. Okay, so this mirror, if you see, it tilts in different directions now. Look, yeah. So this is a chip look like. So and this is a mirror now that can be tilted in different directions. Okay, so you can see how this is a silicon. This is made out of a silicon chip, and the mirror is as big as size of 2 mm or 1 mm kind of a dimension that is possible here. And this is actually very slow in showing, but this can happen at much higher speeds, because this is very light weight and low volume and low mass kind of a mirror that is being moved. Okay, so this is 3.6 mm diameter with a big size mirror, so to say. Okay, and so this is driven by these comb actuators. You can see here. Comb actuators are micro machined on the surface of silicon wafer. It's SOI kind of a technology that they are using, silicon on insulator kind of a technology, and then they get these chips, and these chips are available in market for purchase. Okay, and these chips can be purchased, and we can start playing around with them to get some interesting applications going around. So I'll show you some of the applications people have developed. Okay, with these chips now. And one of them, I mean, I know is in Samir here. Can you see my presentation now?
Yes, sir.
Yeah,
You can see, sir.
Okay. Yeah, I'll get in full screen mode here and see this. Yeah. Okay. Let me move this side here. Okay. Okay. So so let's see some of the applications of this. Okay. So this is a retinal imaging. Like, okay, see, this chip is inside this small little box here, and then the chip is scanning an eye of a person here. Okay, so there is something called OCT. Okay, optical coherence tomography, that is done for the imaging of the retina of the eye and what is below the retina. Okay, this is OCT actually is used to look at some things which are below the retina. Okay, which are normally not visible by a naked eye or by microscope also. that something underneath can be done by this OCT kind of a method. Okay, there is a lot of processing. I mean, there is a lot of theory about how this OCT works, which we should not get into. But here, this OCT is carried out where this optical beam is steered by these micro mirrors to scan a person's, the retina in a very portable and very easy way. Otherwise, this is a quite bulky unit that one has to sit and then do these OCT things. So this is like a portable OCT that is possible now. These doctors can carry to the rural area and then they can get this OCT imaging done for patients in the remote places. So it has a low power consumption and these kind of key features are there. Okay, then there are MEMS microphones. That is another kind of application for. So instead of having a single kind of what do you say diaphragm, you have like a multiple kind of diaphragms or chips which are oscillating, or multiple kind of things are oscillating, and they are sensing or producing sound. Okay, so sensing and producing sound, both could be possible. Microphone will be sensing, and then the sound can be produced also by putting them in vibration, and cavity to amplify. Yeah. Then these are some kind of micro robots people have developed, and this is a very early development where heat actuators are used. They are called heat actuators. Okay, where the relative thermal expansion of two members is used to like a bimetallic strip kind of arrangement, or same metal but multiple thicknesses. Okay, when it passes through, you will have a heating differential happening in a big area to the small area, kind of a cross section current flowing in that. Like the small area cross section will have a high resistance and it will get heated faster than, and then you'll have the actuator bending taking place without even having two materials. Okay, in MEMS you'll have like single material kind of a actuator can be possible then. These are like microfluidic devices used for many different applications. Okay, there are a lot of applications. We may not have time now to talk about them. It's already 10:24, so maybe we'll see some of them in quick kind of a sense, and then we'll move on. So this is you can see this droplet that can be moved by digital kind of electrodes. Okay, so these are the electrodes that are coming here, and you actuate some of the electrodes, and then the droplet starts moving in that direction. Okay, this is based on the principle which is of the kind where the based on the electrostatic field or based on the electric field, the contact angle of a liquid droplet is changed. Okay, and that kind of drives this application. So then there are these micro mechanisms which we develop some of these micro scale logic gates kind of a thing, and or logic gates we have developed in our lab. This is again by using this SOI technology, but this is SOI MEMS kind of so it's not fabricated in our lab, but it is by this MEMS technology. Then flexure mechanisms are used in a lot for these MEMS devices. For example, you see this comb or these actuators. They are guided by these compliant mechanisms here. So you see this double parallelogram compliant mechanism is used to guide this stage here. Okay, so these are used as actuator guides. So this good to know what is this concept of compliant mechanisms for these flexure guides is. Where if you take a single beam, we know that okay, it has this kind of a parasitic error in the rotary direction and axial direction. But actually, I want this this stage to move exactly in a straight line fashion in a vertical direction. How do I do that? I add one more beam to it, and then when the deformation happens here, I see that the tilt is taken care of, but there's still this small parasitic error is still there. And so this is like a single parallelogram kind of a mechanism. And then we use double parallelogram then both the things happen. Like, you know, so now if you just say that, okay, this stage is not there, only the blue stage is there, and you deform that, and then you'll find that, okay, it will deform as this previous figure, and then this parasitic error will be produced in this front direction, okay, and then this green block motion is producing parasitic error in the opposite direction, and they will balance each other, and, like, you know, you'll have this motion happening perfectly in a straight line kind of a fashion for this green block. Okay, and that is what is used in a lot of these compliant mechanisms at a MEMS scale to drive, like, you know, or guide. So you know, instead of, like, you know, having a ball bearing kind of a guide that we have in the larger scale, it is not possible at a MEMS scale to have, like, you know, some kind of a friction based guide. Okay, either bearing or, like, you know, other kind of a friction. You don't want to have that kind of a friction existing. Otherwise, a lot of wear and tear will take place, and then those devices will be non-functioning in no time. So that's where you use this kind of a, you know, compliant beam guides actually. And we have designed some kind of a nano stages at IIT Bombay. These are again, like, you know, the research way back maybe 10 years ago kind of stuff. Okay, and then there are some of the other biomedical applications. I think maybe in the interest of time, we'll just stop here. There are a couple of other applications that are happening. I'll touch upon some of them when we talk about the fabrication for MEMS. This is one of the interesting applications that we are also developing at IIT Bombay. We are developing actually machine to, like, you know, fabricate these micro needles in some very innovative way. So these microneedle patches nowadays are getting kind of popularity. You want to like, you know, deliver either injection or like a vaccine or some kind of a thing. You put a drug into these microneedles, and it is based on the principle of mosquito, how the mosquito bites. You don't even feel that mosquito is biting you much actually. So it's very small little needle that goes into your skin, and it penetrates and delivers drug there. You'll not even get to know that, okay, it is happening. Okay, so the pricking of the skin for your blood sample or that is prevented here, for the drug delivery, that is prevented here. So there is a controlled delivery that will happen for the drug in this case, and one can self-administer drugs. You know, you can just put this patch on the surface of your skin, and then, like, you know, the drug will keep on getting delivered into your system. Okay, so this is one of the interesting applications for micro needles. And by the way, these micro needles are not really hollow needles. Okay, they are made up of polymer and some kind of a drug themselves. So this polymer is biocompatible. It gets absorbed into the body, and as it gets absorbed, like, you know, your drug is getting released in the body. So it is very slow release of the drug can be happening with these microneedle patches. So you put a patch for 2-3 days, and then, like, you know, the drug is getting delivered, you know, over a time very slowly, and that is more effective, by the way. Instead of, like, you know, suddenly having increased dose of the drug in your bloodstream by using your injection normal way, and this is a very easy way to do stuff. And this is going to become popular in the future as we have the social distancing and other norms coming up. Now that will become a new norm, new normal now. So this will be popular in the future. Okay, maybe we'll stop here for now, and then we'll continue with the other lecture next, 11 o'clock. Is that okay?
Yeah, yes, sir. Some questions are there, sir, in the chat box. Some few, one or two. You
Yeah,
can
maybe,
answer.
we can take a couple questions, no problem. Yeah. So can somebody help me with the chat box so you can read the question and I can.
Yeah, I can read, sir.
Yeah.
I can read, sir.
Yeah, please.
So one first question, sir. What is the role of coupling in microactivators?
Role of coupling.
Coupling.
So see, I mean, it's so microactuators. I mean, I don't understand the question really. Like, what kind of coupling you're talking about? I mean, that is need to be clear about. So microactuators are used in the at a MEMS scale. Let's say, suppose if you talk of these comb actuators, they'll have this kind of a guide for the linear guide, and then whatever you want to actuate, you can actuate and you can attach it to that. I mean, I don't know what is the coupling that you are talking about here. I'm
So-
not very sure about.
So that he's asking what should be the impedance of actuators for popular coupling.
So we need to be specifically talking about some application, then maybe it is better.
Yeah.
So so for application to application, suppose you want to drive something at very slow speeds, then your mass, whatever inertia that is being actuated, can have a higher mass or higher impedance, so to say, in terms of like the mass. When you talk about the electrical circuit, becomes impedance. So when you are doing like a very small mass, then you can drive at higher frequencies. It's a simple kind of understanding. So impedance, you can think in terms of like, if you want to think in terms of impedance, like for the mechanical scale, like impedance becomes like inductance becomes like a mass. Okay, mass terms becomes like an inductance. Okay, so then maybe that kind of a mechanical electrical analogy for some people may be easier to think through. For mechanical people like me, I mean, I would say, okay, well, this impedance matching is basically inertia, what I'm driving versus what is my actuation capacity. Like that, electrical people can think about it in terms of the impedance or like inductance term, which is equivalent to mass.
Yeah. Yes. So how sensitivity and accuracy will improve in miniaturization?
That's what I talked in the first slide, that the sensitivity will improve because very small energy can give you large deformations or large kind of a deflections or large sensor signal. That's what the sensitivity will be there. Okay, and accuracy, of course, it will depend upon how you calibrate and how you make things robust to other noises and other stuff. Okay, but since sensitivity is high, naturally the accuracy can also be high if you take care of other factors nicely. That's what I would say. Yeah.
One last question, sir. Can we use micro mirrors in stereolithography applications?
Yes, definitely you can use micro mirrors in fact, DLP. Okay, DLP is one way of like that light projection, but now these micro mirrors you can use, but the range may not be so high. It is very good question. Like, say instead of like a galvano scanning mirrors, which has a very high range of motion in stereolithography kind of application, you can use the micro mirrors, but then like the range of motion will be limited. But you can move these lasers here, this laser beam extremely at high speeds. That is definitely possible with the thing. So the motion range of micro mirror, or in terms of angle, may not be, maybe about few degrees only. But galvano mirrors will rotate with 60 degree, 70 degree rotation is very easy for scanning mirrors, which is currently being used. Okay.
Yeah. Okay, sir.
Yeah.
What are the opportunities in mechatronics field? There are a lot of this is a common general question there.
Okay. Oh, I mean, I see infinite possibilities there actually. There is so many opportunities are there. You think about like the problems that so you just look around and like you'll see some kind of a problem that can be solved. Say for example, like just a simple thing which is already existing solution, but when this pandemic happened, like some of our students, like they said, okay, oh look, I'll develop a simple thing to when I put my hands down there, like it will first give me some soap automatically, and then like it will get dispensed out of some kind of a dispenser by using a relay, and then once I kind of like some time is passed, automatically the water will come on my hands. Okay, so that kind of a system of some of our students developed. So there is like there is a huge scope of mechatronics. I mean these days. By the way, I just should mention that there is a one course in NPTEL mode I'm teaching called Design of Mechatronic Systems. Okay, it has an optional hands-on part to it also. So you can buy some kit that we'll recommend to buy, and then you'll kind of carry out your experiments, and you'll have some support for that in terms of videos. But this is an NPTEL course that anybody can take without fees actually. And somebody, if you want to register and like get a certificate, then some kind of a nominal fees of around some 1,000 rupees is there. So do take advantage of this. Many students can also be maybe like some in your institutions can benefit from this such a kind of a course. They enroll it. See, I know some of the institutions they have contacted me to say that okay, we want to make this course as a part of their elective offering to people. Nowadays, now you can these NPTEL courses can be credited also. So that system can be your system can be like approving these kind of a courses to take it as a credit course, and then your students can benefit from both sides actually. They'll get a knowledge also, and they'll get some credits for their extra learning also. So do look for this design of mechatronic system kind of a course, and maybe I'll give you some. I'll post things to Professor Basu, and
Yeah.
he can kind of pass this this information to all participants.
Okay, sir. Thank you, sir.
Yeah. Okay, great.
So, then we will take one break, sir, for 20 minutes. We will back by 11 o'clock.
11 o'clock. Yeah, sure. No problem.
Okay.
Okay.
Thank you,
Yeah,
sir.
thank you. Bye.
Dear participants, you also can take break. Please come back by 11 o'clock exactly time.
Bye.